Let's continue now. In the last video we looked at maximal ideals. So I'm going to continue discussing them and also solve some problems in this video. So remember, maximal ideals are ideals which have no ideals that contain them properly, and those ideals are proper. So if any ideal contains them properly, then it must be the full ring. Okay, so then obvious easy exercises for you, some to begin with. Just like we had the notion of integral domains which characterize prime ideals, there is an existing notion which characterizes maximal ideals, which is exactly the notion of fields. So the point is, so the two exercises I will write here. The zero ideal, so in fact let me write it like this. I is an ideal of R is maximal, so R is any ring here. So I is an ideal which is given to you. It is maximal if and only if R mod I is a field. So let me tell you how to solve this, and as a consequence of this, let me make another statement first. As a consequence of this, the zero ideal of R is maximal if and only if R is a field. So this can be done more directly, and in fact both problems are a consequence of the correspondence theorem that we have done. So use the correspondence theorem which tells you how ideals of R that contain I are in bijective correspondence with ideals of R mod I, right? This is a theorem that we have proved. If you simply take the canonical natural map from R to R mod I and look at the image of an ideal in R mod I, this gives you a bijective correspondence between ideals of R that contain I and ideals of R mod I. And we have to use this, and also this fact that, so this is first fact. Other fact is R is a field. This also I mentioned before, if and only if R contains exactly two ideals. R is a field if it contains exactly two ideals, namely the zero ideal and R. Remember, every ring contains two ideals, 0 and R. It is a field if and only if these are the only ideals. So this immediately tells you how to solve problem 2, right? Because if R is a field, then 0 doesn't have any ideal that contains it other than the full ring, and the zero ideal also. So it's certainly a field. Similarly, if it's a field, if the zero ideal is maximal, that means there is no other ideal other than 0 and R. So this immediately gives right? This immediately gives 2. And in fact, now using the correspondence theorem, you get 1. There is no problem now, because R mod I is a field by 2 if and only if zero ideal of R mod I is maximal. But zero ideal of R mod I is maximal if and only if I contains no ideal, no ideal contains I. So basically, maybe I should explain this in more detail. So proof of 1, solution of 1. So remember, what are we trying to show? I is maximal if and only if R mod I is a field. So suppose I is maximal. Suppose I is maximal. Then consider, so to show, we want to show R mod I is a field. Now it's enough to show by the property I wrote earlier, it's enough to show R mod I contains exactly two ideals. In other words, the set here ideals of R mod I is exactly two element set, namely the 0 ideal of R mod I and the unit ideal of R mod I. But in other words, we want to show that ideals of R that contain I are also exactly 2. But this is clear now. This will follow if we show that there are exactly 2 ideals of R that contain I. This is true by definition of maximal ideals. This is true because I is maximal, right? So the only 2 ideals that contain I, remember this is another way of saying something is a maximal ideal. The only 2 ideals that contain a maximal ideal are the 0 ideal, that ideal itself and the unit ideal. So that is true. Hence there exist exactly 2 ideals that contain I in R. Hence their images, which are the 0 ideal and R mod I, are the only 2 ideals in R mod I. So R mod I is a field. So if I is maximal, R mod I is a field. Conversely, suppose R mod I is a field. Again, there are exactly as before. So this I will leave for you. Just start the solution and I will leave it for you. There are exactly 2 ideals of R mod I. Because R mod I is a field, the only ideals are 0 and unit ideal. So there are exactly 2 ideals of R mod I. Now we know that this set has 2 elements. So this set, ideals of R that contain I, has only 2 elements, namely I and R. So I is maximal. So I will let you finish this exercise, finish the argument. In fact, I have done it, but if it's not clear, think about the argument and finish it. So this is a way to characterize maximal ideals of rings. Just like we knew how to characterize prime ideals of rings, remember, are those ideals whose quotient ring is integral domain. Here maximal ideals are those ideals whose quotient ring is a field. Okay, so this tells you how to compute, how to find whether an ideal is maximal ideal or not. Okay, so now, let me look at some other exercises. Before that, the question that we should ask even before doing any exercises is, do prime ideals or maximal ideals exist? Do maximal ideals exist in any ring? Right? So do maximal ideals exist in any ring? If you show that they do, then certainly prime ideals also exist, because we know from the last video that maximal ideals are prime. So, and this is a theorem which uses something called Zorn's lemma, which maybe you are familiar with. So I am going to quickly recall it and prove it, but this is not really an important proof. The statement is important. Every ring, remember rings for us are always commutative rings with unit. So every ring contains a maximal ideal. In fact, we will show the following. So in fact, we will show a stronger result. What is a stronger statement? Theorem, let R be any ring and let I be a proper ideal. Proper ideal, remember, means it is not equal to R. It can be 0, but it's not equal to R. So let I be a proper ideal. Then I is contained in a maximal ideal of R. Right? So I am saying that every proper ideal is contained in a maximal ideal. This will show that every ring contains a maximal ideal. So This is because, so of course I assume that non-zero rings. So I'm always going to consider non-zero rings. So every non-zero ring contains a zero ideal, of course, and the zero ideal is a proper ideal because the ring is not the zero ring. So now by the second theorem, the zero ideal is contained in a maximal ideal, so there are maximal ideals. So why is this? So think about how to prove such a statement. Suppose you are given an ideal I. You want to show that it is a it is contained in a maximal ideal. So how do we start? So suppose I is maximal, then you are done, because I is a maximal ideal and I contains I. So I is contained in a maximal ideal. If I is maximal, you are done. Suppose I is not maximal, then by definition of not being maximal, I is contained in a bigger ideal. May not be maximal ideal, but I is contained in a bigger ideal. So this is the idea of the proof. So if I is maximal, we are done, right? Because then certainly I is contained in a maximal ideal. Suppose I is not maximal. So if I is not maximal, implies I is contained in J, right? By definition of a non-maximal ideal, it is contained in a bigger ideal. So J, if it's maximal, we are done. So we are done. So let's actually call it some I1. We are done if I1 is maximal. Okay? Because I is then contained in a maximal ideal. If not, if I1 is not maximal, then I1, so we have I in contained in I1, which is contained in I2. So I2 is a bigger ideal. If I2 is maximal, we are done, otherwise you continue. So you can keep doing this. And you would think that at some point you will stop and get a maximal ideal. Now in mathematics, this is a subtle point. You cannot argue that maybe it will always stop, maybe it forever continues. Why do we know that there is a point at which we can say that this process ends and we do get a maximal ideal? So there is something called Zorn's lemma. So this process may continue forever, right? So we have no reason to assume that it does not continue forever. So there is a tool that we use called Zorn's lemma, which is going to tell us that we can go around this problem and get the maximal ideal that we want. Zorn's lemma, so I don't want to now from this point in the next 10 minutes, I will do some, I'll recall what Zorn's lemma and I'll tell you how to use it to show the theorem that every proper ideal is contained in a maximal ideal. But this is only for people who have seen some of these things before, and if not, this is maybe you can listen to it, but it's not important. The main statement is the theorem, and the statement that every ring contains maximal ideals is something we will know, we will use later. The proof is not that important, so if it's not clear to you, don't worry about it. Zorn's lemma says that, so I'm going to use some notation from set theory. So let S be a partially ordered set. So that means there is an order on this, but it's a partial order. That means not every pair of elements can be compared. In that, let A be a totally ordered subset of S. That means every two elements of A can be compared and say, you can say one is bigger than the other. S is only partially ordered, but A is a totally ordered set. Okay, in fact I should maybe say that, assume that A has an upper bound. Okay, so the statement is that A has an upper bound for every, so I should not really write, I should really say assume that A has an upper bound for every totally ordered subset of A of S. So S is a partially ordered set in which every totally ordered subset has a upper bound. That means there is an element of S which is bigger than everything in S. That's what an upper bound is. Then S has a maximal element. This is Zorn's lemma. So again, I'll remind you, this is only if you know a little bit of this and it makes sense to you. Otherwise, this is not really part of ring theory, so don't worry about it. S has a maximal element. So we will use this lemma. This is an axiom in mathematics that you assume that this is true. So now we apply Zorn's lemma to the following set. So S to be the set ideals containing I. Proper ideals. So I should write that. Proper ideals containing. So I forgot an important assumption in Zorn's lemma. It is a non-empty partially ordered set. So S is not empty. Okay, so otherwise there is no statement you can make that S has a maximal element. Empty set has no maximal element. So we need S to be non-empty. So certainly in this application S is non-empty because I is a proper ideal by hypothesis. It contains I, so I belongs to S. So I am considering all ideals that are proper and that contain S. And we are done if we show S has a maximal element. Why is that? Okay, before that I should really say, so this should come before actually. Consider the ordering given by, consider the ordering on S given by inclusion. So in other words, we say that so some two ideals in, so let's say J1, J2 are in S. We'll say that J1 is less than or equal to J2 if J1 is contained in J2. So this is how you give it a partial order. Remember, this is only a partial order because not every pair of ideals may be compared. Maybe neither contains the other. So, but it's a partial order. We can compare them and this ordering has the usual properties. So now, if we show that S has a maximal element with respect to this partial order, we are done because if S has a maximal element, that must be a maximal ideal of the ring, because if not, there is something bigger that contains it. So suppose M is a maximal element of S. That means there is nothing in S that's bigger than M. That is, there is nothing, so I'll just write it informally like this. There is nothing in S that is bigger than S, M. Right? So M is a maximal ideal of the ring itself. Why is this? Because first of all, first M is proper, right? That is clear because M belongs to S, and S, remember, is the set of proper ideals that contain I. So it is proper. So suppose M is contained in J and J is contained in R. Then remember, J is also in S. So suppose J is not equal to R. Suppose J is not equal to R, we will show that J is equal to M. If J is not equal to R, then J belongs to S because J is a proper ideal. Remember, I contains M. I is contained in M. So J is contained in M. Sorry. I is contained in M, M is contained in J, so J contains I. So, and J is a proper ideal, so J is in S. But since M is maximal element of S, and J is bigger than M possibly, but it cannot be, right? So J is equal to M. So if we show that S is a maximal element, then we are done. And this is where Zorn's lemma comes in. Zorn's lemma says that, gives you under some conditions a partially ordered set as a maximal element. What is that condition? Every totally ordered subset must have an upper bound. So let's take a totally ordered subset. So let A be a totally ordered subset of S. So we want to show that A has an upper bound. Then we are done. Then Zorn's lemma says that S is a maximal element, and we argued that any maximal element of S is in fact a maximal ideal of the ring. So let A be a totally ordered subset of S. Now I claim that, consider this ideal J, define it to be union of all ideals in A. So I take J to be union I prime, where I prime is in A. So now claim is J is in S and J is an upper bound of, I am working with an arbitrary partially ordered set, arbitrary totally ordered subset A of our set S. To apply Zorn's lemma, I need to show that A has an upper bound, and my claim is that this J that I defined is an upper bound. So I need to prove that J first of all belongs to S. So what is S? If you recall, S is the set of proper ideals that contain I. So we'll first show that J is in S. First of all, J is a proper ideal of R. Why is this? J is a proper ideal of R because if it is not proper, what is the meaning of not being proper? If it is not proper, then 1 belongs to J, right? That means J is the unit ideal, so 1 belongs to J. But J is the union, set theoretic union of ideals of A. So 1 belongs to some ideal of contained in A. So that is, there exists I prime in A such that 1 is in A I prime. But this is a contradiction, right? Why is that? This is absurd because A only contains proper ideals. By definition, S contains only proper ideals. So A contains only proper ideals. So in particular, I prime is proper. So I prime cannot contain 1. So J is a proper ideal. Sorry, actually, we don't yet know that it is an ideal. So I'll say that J is a proper subset, I should say, of R. J is a proper subset of R because if it is not, then it is equal to R, then it contains 1, and we showed that that cannot be. Second point is J is an ideal. So we have 3 words here in S. It is a proper, ideal, contains I. So we showed that it's proper, we will now show it's ideal, then we will show it contains I. So J is proper, that is correct. Now we show that J is an ideal. Why is J ideal? This is the most interesting thing, and in fact this is where we need that capital A is totally ordered. So remember what is an ideal. So if 0 certainly belongs to J because 0 belongs to every element whose union is J, I prime. So now on the other hand, suppose A comma B are in J. We want to show that A plus B is in J. If A comma B is in J, then A is in I1 and B is in I2, where I1, I2 are in A. Right? A is a collection of ideals union of all the ideals that are contained in A is J. So if two elements are in, if an element is in J, it must be in one of them, one of the ideals of A, because J is the union of all ideals of A. But now since A is totally ordered, I1 is contained in I2 or I2 is contained in I1. This is not true for a partially ordered set but true for a totally ordered set. So suppose this happens without loss of generality. This happens, then A belongs to I1 which is contained in I2, B belongs to I2. That means AB belong to I2, but I2 is an ideal. That means A plus B is in I2. But that means A plus B is in J, because I2 is contained in J. J is the union of ideals in, I will write it again so that you can see. J is the union of ideals so I2 is an ideal of A plus B is in I2, so A plus B is in J. Similarly, you can conclude, this is more easy, if A is in J and R is in R, then RA is in J. So J is an ideal, that is okay. So, and finally J contains I trivially, right? This is trivial. Why is this? Because every ideal in A contains I by definition, right? Because our whole set capital S is things that contain I, and A is a subset of S. So every element of A contains I, their union also contains I. So J is in fact going to trivially contain I. So what did I show now? J is in S, and yeah, so what I have shown is that J is in S is what we have shown. Hence J is in S, is an element of S. Remember, S is a collection of ideals, J is an ideal, so J is contained in S. And clearly this is very easy, J is an upper bound of A, because remember J is the union of all ideals in A. So if I prime is in A, then I prime is contained in J, because J is the union of all ideals in A. In particular, I prime is one of the things that contributes to that union. So J contains I prime. That means I prime is by definition of the order on S, I prime is less than or equal to J. So every element of A is less than or equal to, maybe it's equal to, we don't need to know about that, less than or equal to J. So J is an upper bound. So in other words, we have verified the hypothesis of Zorn's lemma. Now Zorn's lemma says that S has an upper bound, has a maximal element. It's not an upper bound of S. Remember, I'm not saying that every element of S is less than that maximal element. I'm saying that there is nothing bigger than that element in S. In other words, I is contained in a, this I argued earlier, I is contained in a maximal ideal of R. So in conclusion, every ring contains maximal ideals and hence prime ideals. So this is good to know. So because maximal ideals are prime, so every ring contains maximal ideals I have shown, hence every ring also contains prime ideals. So now what I will, so I'll end the video here, but let me just remind you again that the upshot of this video is that we have learned that how to characterize maximal ideals. These are ideals such that the corresponding quotient ring is a field. And similarly, in a commutative ring, something is zero ideal is maximal if and only if the commutative ring is a field. And rest of the video we spent proving that every ring contains maximal ideals. So now this proof itself is not that important. If the proof is not clear, you can think about it and you can ask questions, but this is not required for the rest of the course. The statement is only required that every ring contains maximal ideals is needed, but the proof is not needed. Thank you.